All right, now we're on to esters. And the first reaction we're going to talk about is ester hydrolysis. So hydrolysis, we are adding water to the ester, forming the carboxylic acid, and giving off the methanol in this case because it's a methyl ester. So first off, which side of this reaction is favored? We should think about it the same way we have all the other reactions. And you've done that. You already paused the video, you did it, you came back. Which side is favored? Neither side's favored, right? We got two reactants over here, two reactants over there, or two products over there. That means entropically we're pretty neutral. And the bonds that are being formed, all those sigma bonds that are being formed, are the same as all of the sigma bonds that are being broken. So really, entropically, enthalpically, we're pretty neutral on each side. So what is driving this reaction one way or another? This is kind of the same situation so esters to carboxylic acids are the same situation as the carboxylic acids to the esters. It's just driven by an excess of the reagents. So if we want to push it backwards to this side, we have an excess of the alcohol. If we want to push it forward to the carboxylic acid, we have an excess of the water around. So in ester hydrolysis, excess water is used to drive the reaction forward. Mechanistically also, I want you guys to just pause the video and do this for yourself. This is the same exact thing that we just saw for carboxylic acids being transformed to esters. It's the same exact conditions. It's called the principle of microscopic reversibility. Essentially, if a reaction happens by specific steps in the forward direction, those same steps are going to be followed in the reverse direction as well. So you've already done that. You've figured that out. What happens in the first step? It's just a proton transfer from our acid catalyst to our carbonyl oxygen. That makes that carbonyl carbon a stronger electrophile. And again, sometimes I mess up, but all of these arrows should be equilibrium arrows. All these steps are in equilibrium. So that happens. That makes this a very particularly electrophilic carbon because that oxygen and that oxygen are pulling electron density away from it. Last time I showed this in two steps where I showed the resonance structure and then the water added to the resonance structure or the alcohol added to the resonance structure. This time I'm just going to show it in a single step. That adds there while those electrons go up to that oxygen. So that would provide our tetrahedral intermediate. And at this point we have our really acidic hydrogens off of the oxygen that just added in. If these electrons collapse back down, forming the tetrahedral intermediate, the best leaving group at this point would be the OH2. But that hydrogen can be transferred to any oxygen really that it comes into contact with. One of those oxygens would be the oxygen that is right next to it. So we could transfer the hydrogen there. That makes it a substantially better leaving group. So at that point, this is the best leaving group, and as that carbonyl reforms, it would kick out that methanol molecule. So that's what we have right there. What else would form is the protonated carboxylate, that oxonium ion. And at this point, again, any neutral oxygen could be used to deprotonate that acidic proton. What's around in the largest quantity? We're pushing the reaction that way, so the largest quantity is water. So we'll just show water deprotonate this in the last step to form that product. And again, I forgot the equilibrium arrow there, just added it back in. So again, if you look back at going from carboxylic acids to esters, it's the same thing. So make sure you can kind of reason out the different steps of this mechanism. Okay. All right, so now we're going to look at how base can be used to go from esters to the carboxylates slash carboxylic acids. And that's what we have here is a carboxylate, so the deprotonated carboxylic acid. In your note packet, I actually have the protonated carboxylic acid. That is a typo. So in your note packet right here, oh, it's so hard, it's backwards. That should be the deprotonated anion as I have indicated it up on the board there. So this is base promoted. Let's come back around to discuss why we say promoted. What we said earlier for the other version was acid catalyzed. This is base promoted. So let's think about maybe what that means soon. But we have some hydroxide around, some OH minus. That is a strong base slash nucleophile, right? In the acid catalyzed ester hydrolysis, we only had water as our nucleophile. Here we have O minus, a much stronger nucleophile. In the acid catalyzed, because we didn't have a strong nucleophile, this oxygen had to protonate to make that electrophilic enough for a nucleophile to add. But in this case, again, we have a strong nucleophile, a strong base. So it doesn't need any help. It is a strong enough nucleophile to immediately add to that carbonyl carbon. Again, in an equilibrium sense. So that's going to occur, making this tetrahedral intermediate. And at this point, we don't have any proton transfers needed. We could theoretically transfer this proton from there to there, but that would get us to the exact same place. Can we transfer our proton to this oxygen? We can't do that because this isn't a very strong base or nucleophile. It's neutral. This one being negatively charged, that means that it is a lot stronger as a base, stronger as a nucleophile, so it could theoretically grab a proton from water or a neutral OH. But in any case, that could happen. Doesn't really matter if it happens or not, but we're forming this tetrahedral intermediate, and those electrons are going to collapse back down to form the carbonyl. And at this point, we have to ask ourselves, well, what's the better leaving group, OH or OCH3? What do you guys think? Take a minute. Yeah, they're about equal, right? They're both negatively charged oxygen molecules, so they're going to happen with about the same probability. So if this OH is what leaves, that just takes us back to the starting materials. But if this OCH3 leaves, that progresses us forward to a carboxylic acid and OCH3 minus. Okay, so at this point, we have our OCH3 minus around. We have this carboxylic acid. Why is this carboxylate the product that I should have put in there instead of this carboxylic acid? Well, this is an equilibrium step, this is an equilibrium step, but this step is very much downhill. Why is that? If you can't think about it, pause the video for a second, try to think about it. So, equilibrium arrows, unidirectional arrow, why? Okay, yeah, because it's an extremely downhill acid-base reaction. This is a carboxylic acid, pK around 5. This right here, the conjugate acid, is an alcohol, pK of around 16. So we're moving away from the stronger acid here to the carboxylate product. Okay, so back to our original question when I underlined this, base promoted. Acid catalyzed means that the acid is used and it's reformed at the end. Why is this called base promoted? It's called base promoted because we need a full equivalent of our base. The base is used here. It kicks out something that we would also call a base. This is a strongly basic thing. But whether it's OCH3 minus or OH minus that does this last proton transfer, we are using up a full equivalent of our OH minus. So it's promoted because the base is required for this reaction to occur, but it's not catalyzed by base because catalysis infers that we are reforming the catalyst at the end, and we're not reforming OH minus. That OH minus is fully used up, so it's promoted by that base. Okay, more ester reactions. All right, so what else can we do with esters? So we can take esters to carboxylic acids. We should also be able to make the most stable carboxylic acid derivative amides from esters, and it turns out we can't. Esters will react with amines to make amides. What's this big blank for? Usually, right? The most stable, we'll just write most stable carboxylic derivative. So esters will react with amines to make most stable carboxylic acid derivative amides. This is a very downhill reaction because we are forming the most stable type of derivative of carboxylic acids. So how's this going to work? Well, we have our amine over here. We have our ester. Amines are basic and nucleophilic, even in the neutral state. So that can just simply add in here immediately. That would produce that same type of tetrahedral intermediate we've seen throughout this chapter, and essentially at this point there's more of our amine around, and that can actually grab a proton from this NH2 because it's actually a pretty good leaving group as NH3. It's a really good leaving group as NH3. It's really stable by itself. But once another one of these grabs that, that produces this intermediate where the NH2 is now a really poor leaving group. So at this point, and this is a unidirectional arrow, we could say that this is a equilibrium arrow, but this is pretty downhill as far as the acid-base chemistry here. So at this point, the tetrahedral intermediate can break back down, kicking out the OCH3. That produces our amide product and also OCH3 minus. So one thing that you notice is that compared to, say, the acid chlorides going to amides, we said we needed greater than 2 equivalents of our amine. I didn't say that this time. Why is that? Okay, you answered, you thought it through, you've kind of drawn something about it. That's good. We don't need greater than 2 equivalents of it because once we expel this OCH3 minus, it's actually a really strong base. So the pKa of ammonium, one of them you should know, is 9. So I'm going to take off this 4, I'm going to draw a 3, and put the 4th one right there. So this acid-base transfer that I will draw in right here is really downhill. This guy here has a pKa around 16. So we went from the stronger acid to the weaker acid, a downhill reaction, to regenerate our amine, which allows it to act as the nucleophile in this reaction. So esters, we can go from esters to carboxylic acids, either with acid catalysis or base promoted, and we can also form amides. So pretty neat.